Good evening, everyone. Good evening. I'm Dominique Lazarski, and I chair Uecna, the European Union Against Aircraft Nuisance, an NGO representing citizens before the European institutions. Welcome to all of you attending our new webinar today, dealing with aircraft noise, which has been the subject of various webinars, which are already on our website and which you may watch again if you missed them. I would also welcome those who will watch the replay of this on our website. And we know we now have friends in the Americas, from Canada to the US and Brazil, but also from very far away, is like India or Australia. The industry tells us continuously that aircraft have tremendously reduced their noise emissions and will continue to do so. It is true that new aircraft emit less noise than older ones, but we are more and more annoyed by aircraft noise. The repetition of noise events, which have increased with the boom of the traffic, and also because of the renewal of the fleet, which is a slow process. The European Aviation Environmental Report confirms that noise impact of aviation is increasing despite the improvement of technology. But what about the future? Are citizens going to benefit from new technology? Is aviation noise really going to decrease as promised? Is a noise reduction compatible with the new technology aiming at reducing greenhouse gas emitted by aircraft? Let's hear what our speaker of today has to say. Eleftheria Emfiezi, a health expert from Athens, climate ambassador in Greece, and treasurer of Uecna. You have the floor to present Finlay Asher.
Thank you, Dominique. Good evening, ladies and gentlemen. Today with us is Mr. Finlay Asher, who has a degree in mechanical engineering from Edinburgh University. Mr. Finlay has spent 7 years working at Rolls-Royce on aircraft engine design. He is also an activist, and he now runs an organization called Safe Landing for climate-concerned aviation workers. Mr. John Stewart and our colleague Giulio Marcelli will facilitate the discussion and the questions afterwards. And Mr. Asher, the floor is for you.
Thank you. Cool. I'll just share my screen. So, yeah. So, the title of this talk is Fuel Efficiency versus Noise, and it's really about, can we continue to make aircraft more and more efficient and also more and more quiet at the same time, or is there going to be some challenges that come along with that? And I'm going to present some of my experience working on aircraft engine design. And I'll just start by giving you a little bit of my background. So I'm a mechanical aerospace engineer. I now run this group called Safe Landing, which is for climate concerned aviation workers. We think that the growth of the industry is actually dangerous for jobs. And we want to see our industry telling the truth about the impact of aviation and what's possible with technology and what sort of policies we need. I've also got a YouTube channel called Green Sky Thinking, which explains a lot of the technology greenwash that you see in the industry in some short kind of 3-4 minute videos on different topics. And I've got hyperlinks there if you want to check those out. And I spent 7 years at Rolls-Royce. Rolls-Royce are the second biggest aircraft engine manufacturer in the world. And I was working on future aircraft engine design. So just a little bit about that. I was working, a lot of it was in future technology, in the future programs teams. So looking at future Airbus and Boeing commercial aircraft in the kind of 2030s timescale, 2020s, 2030s. So kind of like, it's called the Vision 20 team, looking at kind of 20 years into the future and what's coming next. So within that work, and also I was kind of working in system design at the whole engine level. So I got a good understanding of lots of different interactions that are happening around the engine and different trade-offs. So one of the first concepts that I was working on is called the Ultrafan, and this is a geared turbofan that's got a gearbox in it, and I'll talk more about that in later slides and some of the challenges there around noise and other things. And then also the variable pitch fan, which is fan blades that can move and change the pitch angle of the blades to optimize themselves for different stages of flight. And yeah, when I was in the company in 2019, after actually Extinction Rebellion and various groups put more pressure on the government and there was climate emergency declared, there was a real increase in messaging about sustainability strategy from my company and other companies in the aviation sector. And I started a group internally to challenge some of the stuff that was being said in the media and to politicians, and try and apply some reality to it and push for change from within. But yeah, I decided to quit my job about a year and a half ago, and I've done environmental campaigning since then, being involved with airport expansion, and also founding this group called Safe Landing, which is for climate concerned aviation workers. And we believe that workers need to navigate a different future for the industry that's truly sustainable, and will provide secure and sustainable jobs as well. And yeah, I'll provide kind of our email address and our website at the end so you can check us out. So why, just in terms of this talk, the fuel efficiency versus noise. So there's something called ACARI, you might have heard of this, Advisory Council for Aviation Research and Innovation in Europe, bit of a long title, they called it ACARI, and they've got these Flight Path 2050 goals, and their aim is to reduce CO2 per passenger kilometre by 75%, and to reduce perceived noise by 65%. And that's relative to a year 2000 aircraft. So there's these, and there's also like NOx targets and other things. But actually, like, there's a question here about, is it possible to achieve these things at the same time, and actually is there conflicts? And also, if you look at airport expansion, often an airport will claim it's increasing the number of aircraft, but overall emissions will go down because of efficiency improvements, and also noise will go down. And are those two things really possible, or is it going to be quite difficult? And that's what I'm going to explore here. So I'm going to talk through sort of aircraft efficiency and engine efficiency. And I understand some of you might not have an engineering background, or this might be new to you. And I'm going to try and talk it through in a way I describe like to a new engineer, and hopefully this will make sense. And also you can ask me questions at the end if anything isn't clear. So basically, just like the basics of aircraft design is, in order to move forwards in the sky, you have to produce thrust from the aircraft, which comes from the engines, and you need to overcome the drag on the aircraft from air resistance. You also need to produce lift from the wings, and that's to overcome the weight of the aircraft so that you can increase and climb into the sky and you can stay at altitude. Now, you obviously want to minimize drag, because then you can minimize thrust, and that means you burn less fuel, which means you can be more fuel efficient. So in order to minimize fuel burn, lighter materials are really good. So if we use carbon fiber rather than metal, titanium, that sort of thing, we can reduce the aircraft weight. And that will mean we need less lift, which means we need less thrust from the engines. Also, more aerodynamic aircraft shapes, the wings and the fuselage, mean that there's less drag, and therefore you need less thrust to fly at a given speed, and that's less fuel burn. And also more fuel efficient engines. So in order to get a certain amount of thrust from the engines, if the engine's more efficient, you need less fuel as well. So a lot of the efficiency improvement, though, comes from the engines. It's quite a significant part of it, and that's obviously my background, and I'm going to talk through some of the things we can do with the engines and then some of the difficulties. So just the kind of basics here is, in order to produce thrust and to push an aircraft forwards, you need to create some momentum, and you do that by moving some mass back the way. So it's a bit like a swimmer in a swimming pool. You pull water, push water behind you, and you go forwards. And it's the same with an aircraft, apart from it's air. So you chuck air back the way, and that pushes the aircraft forwards. And you can do that using a propeller, or you can do that using a jet engine, which is called a turbofan or a turbojet. So, and just kind of taking you through that. So in general, so actually, yeah, one of the things is, so batteries and hydrogen have really difficult energy storage requirements. So we use jet fuel in aircraft because it's very high energy density. You get within a certain mass and volume, jet fuel has really high amount of energy. But in order to get the energy from jet fuel, from oil, you need to combust it. And you could do this like in that propeller aircraft there. That's got a piston engine in it from World War II. And a piston engine, there's kind of 4 phases to that. You have to suck air in, then you compress the air, which increases the pressure. Then you ignite, you add the fuel and you ignite it, and that increases the temperature and the pressure and means that you can do work and produce power. But then you need to have an upstroke again to exhaust that gas. So actually you do 4 cycles and only one of them produces power. And it's kind of quite discontinuous. Whereas in a jet engine, it does the exact same thing. You've got an intake, there's then a compressor that compresses the air, goes into a combustion chamber and mixed with fuel where it's burned and you increase the energy. And it goes out through a turbine, and the turbine's just there to extract some power so that you can run the compression stage. And then there's the exhaust, and you've got higher pressure, higher temperature air that you put out through a nozzle, and that accelerates the air and provides the thrust. Now, that means that you can have a really light engine. It's got very high power density because it's continually sucking air in, continually creating thrust, and that's all good. But you've got this very fast stream of a jet stream that's coming out the back, and that's quite inefficient. It's good if you want to go very fast, but you burn a lot of fuel as well very quickly. So you see something like this in a fighter jet. It goes very quick, but it's not very efficient. And that's called a turbojet. And it just creates thrust from the nozzle. Now, if you want to make this more efficient, what you do is you have a turbofan configuration, and this is what's on most commercial aircraft. So you've got the compressor, the combustor, a turbine that drives the compressor. But what you do is you actually take more, as much of the energy as possible out of the turbine to make the exhaust thrust as low as possible, because that's inefficient. And instead you drive a big fan on the front. The fan goes a lot slower and it can suck in a lot more air. And because it's moving a lot more air slower, it's more efficient. Now, the problem with this is the fan is connected by a shaft to the turbine, so they need to spin at the same time. And when you make your fan bigger, it gets faster at the tips, and you can get shock waves when it goes supersonic. So you want a fan to go slower, but when you have a fan that runs slow, your turbine runs slow, and that's an inefficient turbine. So what you can do is you can have a gearbox in the middle. That means you can have a slow moving fan and a fast moving turbine. and that's called the geared turbofan. It allows the fan to rotate slowly than the rest of the engine, and it can push an even larger volume of air around the engine and make it even slower. So that's one of the concepts I was working on as well. So just to explain like the basics of why you do this, this is change in momentum. So change in momentum is mass times change in velocity or acceleration. And the bigger your velocity is, that's all wasted energy. You can get the same momentum if you do a larger mass of air and you move that slowly. And that's much more efficient for the same momentum, the same thrust. You basically, so I'm just moving my camera around so I can see, it's more efficient. And that's kind of why we tend to have these turbofans, and also we make the turbofans bigger and bigger, so we can move a larger mass of air. And this is why you'll see on older aircraft, there's a very small engine, and as the years have gone by, the engines have got bigger and bigger on the wing because that's more efficient. So back 50 years ago, the first commercial aircraft, they had very small engines, and now up past the 2000s, we've got these really large ones when you look at them from the front. So that's increasing engine diameter, means you've got an increased mass of air, and that's a better propulsive efficiency. It's more efficient. But there is a downside with this. So when you increase the diameter of the engine, you make it bigger, that also increases the weight of the engine and the drag of the engine nacelle. And when I say the engine nacelle, that's the covering or the cowl that goes around the engine. And basically there's an intake. The intake slows the air down and pressurizes it ahead of the fan. And that's good because it stops the losses at the tips. And then the bypass is the air that goes past the fan and past the core, and where most of your thrust is coming from. So the problem is if you think about this engine as a cylinder, you make the diameter bigger, you get more air going through, but it's becoming heavier and the drag's increasing. And what you get is you get an increased propulsive efficiency, that's good, but then the weight and the drag start to cancel that out, and you get marginal benefits, and you might make things worse, and you're making it more expensive as well. So, and it's a heavier engine on the wing, so you get this kind of thing where you start to cancel out the benefit. So what we do as engine designers is we start to think, well, this is a cylinder, and we can reduce the volume of the cylinder by making the length shorter. We could try and shorten the engine intake and shorten the bypass duct to try and reduce, cancel out some of that weight and drag increase. So one solution is to reduce the engine length. And I just posted this because this is from the Boeing website, and they're saying smaller nacelle, less weight, lower cost, less drag, and there's a trend that the fans are getting larger, and this is a way of cancelling out. It's called the short inlet testing program, and I was involved with this. But there's a problem with shortening the nacelle. So basically, if you shorten the engine nacelle, you've got a shorter engine inlet, that's this part here, and you've got a shorter bypass duct. And that's the exact area on the engine where you put your acoustic liners, which are the noise damping panels within the engine. So this blue area here, that's your fan acoustic panels. And then you've got bypass duct acoustic panels here as well as some in the turbine exhaust. But this is what you're shortening. So fan forward noise gets damped out by these liners, fan rearward noise gets damped out by these liners. And if you go from your current engine and you make the diameter bigger and you shorten the inlet, you're just shortening the area available for these acoustic liners, and you're kind of eroding the amount of area you've got there to damp out the noise. So this is a bit of an issue, and the bigger we make them, the shorter and shorter it gets, the more aggressive we are with our understanding of the aerodynamics. there's quite a few difficulties there, but a big difficulty is there's just no space left for the noise panels. And this isn't really a problem that we've solved when we're looking at kind of 20 years into the future, because they could get really short. So this is just this kind of trade-off we've got with turbofans as it is. And basically, this is a bit of an engineering chart, but it's showing within an engine, you've got the thermal efficiency from the combustor, and that's like how hot and high pressure you can get inside the core. That improves your thermodynamic efficiency. And then you've also got the propulsive efficiency from the fan and the bypass duct. So if you have thermodynamic efficiency here, and that gets better going up the way, propulsive efficiency getting better going to the right, and then you've got overall efficiency, which is this times this, thermodynamic times propulsive, and you've got lines. And you can see original turbojets started off about 20% efficient. They've moved up through 30% towards 40% efficiency with the latest Airbus A350 that I was working on. And they've kind of circled bypass ratios. So the bypass ratio gets bigger and bigger. So more and more air is going past the core through the fan rather than through the core. And we're now looking at how do we go further. And there's a few different concepts that I've been working on. The geared turbofan, which I showed you already, and a variable pitch fan, and open rotor is another one. And I'm going to take a look at some of those. Although you can kind of see where, we're only going to approach 50% efficiency, and probably your absolute limit is like 50 plus with like very advanced technologies. There's a limit we're trending towards, and it's getting more and more difficult to improve efficiency. So looking at the geared turbofan first, one of the problems with putting this gearbox in is you've got a very large amount of power that's going through your turbine to your fan. It's a huge amount of power. It's powering an aircraft. So even though this gearbox is really efficient, and they're looking at sort of 99% efficiency, even a 1% efficiency loss produces any efficiency loss creates heat. And that's a large amount of heat, and that heat goes into the oil that's in the gearbox, and that adds to your oil system, and you've got to cool that oil down. If oil overheats, then it can coke, and it will harden up, and your oil system will fail. So you need to always keep your oil nice and cool, but you've got this big new oil system requirement. So normally in an engine, a bit of a complex diagram here, but it's showing the oil system, and there's bearings that the shafts run on so that they can spin, and they're lubricated with oil, and you normally need to cool those down. But you've then got an additional big massive gearbox with a lot of high volume of low grade heat, which means you need extra air coolers. And I've just circled, there's air coolers that are in the bypass duct. I'll just switch to this simpler diagram. It basically means you need oil coolers that get cooled by the air in the bypass duct. And you basically need to put these in the same place where you want to put your acoustic panels. So you've now also got this competing requirement for extra cooling. And those coolers need to sit in the exact same place as the acoustic liners. So this is a big challenge as well, moving to a geared turbofan. So next, variable pitch fan. So the reason why we need a variable pitch fan is it's kind of a bit complicated to explain, but a fan has what's called a working line, and it's a region it can operate in before it stalls or before it surges. And the bigger you make the fan, the higher the bypass ratio, the lower the fan pressure ratio. It just means this is more difficult because there's a bigger difference between the engine operating at ground level and operating at altitude. And it means that it's very difficult to keep the fan from stalling without varying the geometry at ground level. So what you need, because basically engines are designed for cruise and then they operate at a higher thrust when they're on the ground to take off. And what you find is it's just impossible to design the engine without providing some variability that changes the area of the flow through the engine. You can kind of do this in two ways. You can have a variable pitch fan where the fan blades rotate, or you can also have a variable area nozzle at the rear of the bypass, and it looks like this. Pratt & Whitney, when they had their first gear turbofan, they thought they needed this, and they just managed to just not need it. But if you go any larger, you will need something like this. And the thing about this is it adds extra weight to the engine and extra complexity, extra failure modes, and lots of design challenges, which mean we don't quite know what the best thing is. But also, anything with variability introduces a feature into the engine that isn't smooth and it's discontinuous, and it needs to be able to rotate. So there needs to be some features there and there, and you can see that there will be gaps. Wherever there's anything like that, it's a potential additional noise source. And this will need lots of work to prove that we're not just going to massively increase the noise. And it will require lots of testing and lots of different configurations. And there'll be a much wider variety of operating conditions, which mean it's harder to specify what the noise is. So these are all challenges as well for these future concepts. So as I was saying, fan pressure ratio is the thing that's getting lower and lower as the diameter gets bigger, because you need to accelerate the air less, so the pressure ratio goes down. And basically, this is a diagram from someone else, but it's just kind of showing as you make the propulsive efficiency greater and the pressure ratio lower, there's a limit somewhere, and it might be around 1.3 or 1.4, but I think it's probably around 1.2, 1.3, where all of these challenges mean that there's just a limit to how much we can improve the turbofan as it is. And that's because of just this increase in weight and drag of the nacelle. And what we're probably going to do is we're probably going to need to get rid of the nacelle completely, because it's just too heavy and it's too large and it's too draggy. And that's where we'd switch to an open rotor concept that doesn't have a nacelle at all. So this is what an open rotor looks like. And it would have no nacelle duct for acoustic panels. So there's no way of attenuating the noise at all around the engine. It also have counter-rotating blades, and this is because if you didn't do that, you lose a lot of your energy as swirl, and you want to take that swirl energy back out and direct it into thrust that's going straight behind your aircraft. So you need counter-rotating blades, and that just means you've got a really complex mechanical design inside there, and you've got complex interactions between the blades. It's also not clear where the best place to put this engine would be, partly because we're really worried about the noise profile of it, because there's no shielding and no liners. We might want to put this engine like above the body of the aircraft, or above the wings, or above the fuselage, to shield the ground from the blades. The other concern is if one of these blades breaks, normally the nacelle provides a shield that contains the blade. We don't have this, so often when you see this design of engine, it's positioned somewhere else on the fuselage, like away from passengers, so that in the failure case where one of these blades fails, it can't go flying into a critical part of the fuselage. So yeah, there's quite a lot of complexity that comes with this design, with a lot of problems that are still to be resolved. But you can see Clean Sky, this is the EU funded program that's pushing open rotor. They really highlight noise and vibration problems of it. When this concept as well was developed in the 1980s, this is one of the reasons the concept was shelved, because of the high noise profile. And the other difficulty, as I was saying, is where to install it on the aircraft. and how the complex wake interacts with the aircraft as well, which is another thing that can create noise. I just realized I've got words over itself. So yeah, final thing really is just where to put this engine. So I'm just giving you a few examples here of different aircraft concepts, and really aircraft designers haven't figured out the best place to put them, and there'll need to be a lot of testing before we can decide what the optimum place is. But a big factor of this is the noise. So you can see that on this concept, they put the engine sort of between the tail fins of the aircraft, and this is to try and shield the ground from the blades. Equally here, this one, it's above the fuselage as well, and this is all because of the noise issue, trying to basically create a shield between the engine and the ground by putting the aircraft in the middle. But also they've tried with a high wing, a low wing, at the back of the fuselage, at the front. You can see some of these are a pusher configuration with the blades at the back. This one has got a puller configuration with the blades at the front. So it's really uncertain. When you've got this uncertainty in terms of the configuration, you can't really start doing the detailed testing to understand the noise profile and all this sort of stuff. So yeah, but this concept is being relied on by a lot of the sort of sustainability strategies for the industry. So just going to give you a summary of what I've talked about, try and wrap it up, and then we can go to questions. So the engine is a major source of aircraft efficiency gains, improvements. Current turbofans increase propulsive efficiency by increasing the engine diameter, but there's marginal gains that can be had because we increase the engine weight and the engine drag. We can shorten the nacelle to compensate, but that reduces the area for the acoustic liners, and that's an unresolved challenge that hasn't been solved yet. And geared turbofans have an additional challenge because they've got these extra heat exchangers which get in the way of our noise liners. And then the variable pitch fan, variable area nozzles could be additional noise sources, and they will be required below a certain fan pressure ratio in the future. It'll be difficult to get away from using them, and that's an additional noise source. And then open rotor can provide a further fuel efficiency improvement, but we lose the nacelle completely, and it's unclear how we then reduce the noise and where to place the engines. So there's kind of these unresolved challenges. And then I thought I'd just give you some other thoughts as well. So if there's a tendency at the moment towards stretched aircraft, so making an aircraft design as long as possible to fit in more passengers and higher load factors, which means for a given aircraft, there's more passengers in there in terms of passengers in every seat, but also the seats as close as possible together. And particularly low-cost carriers like Ryanair and EasyJet really try and shove everybody in economy and get as many people in as possible. That means that for the same aircraft taking off on the same flight, it will have a higher takeoff weight, and greater takeoff weight means we need higher takeoff thrust, and that will mean increased takeoff and climb noise. So you might see, even though the same aircraft might get quieter side by side, you've also got this kind of change to airline operations that's cancelling that out and increasing the noise again. And that's worth thinking about. I also think there's a tendency towards longer range flights, and because we've become more fuel efficient, we can fly further. So the average flight is going further and further. But that means if you fly further, you start off with more fuel on board at takeoff so that you can fly further. That means you've got a greater takeoff weight and greater takeoff thrust required, which probably means that you increase your takeoff and climb noise. Then the final thing is we've got higher day temperatures. Because of global warming, the average temperatures on the surface are becoming higher. And that means that we've got a lower air density at ground level. And that means that you need to run your engines higher to get the same engine thrust, because you need to suck more air through to get the same mass flow, to get the same thrust. And that means likely, I think as well, that we'll get increased takeoff, climb and descent noise as well. Those things probably need explored in more detail, but I just thought if these things are being discussed with the industry, these are good questions to ask them. And I just thought I'd include those as well for completeness. So yeah, that's the end of my presentation. And just to kind of signpost, we've got a website, safelanding.org, and an email address, info@safelanding.org as well, that you're welcome to follow up with any questions in the future, if you're interested in talking to aviation workers about anything where you think we can help. So yeah, thanks for listening, and keen to answer any questions you might have.
Finlay, thanks very much indeed. That was fascinating stuff. And as Elizabeth here said, I'll be facilitating this session with Julio. So as before, anybody feel free to ask a question, either just put up your hand or just, if I don't see you, shout it out. And as I've said several times, this is easy for me because I'm a native English speaker. If you're not, and you're a little bit worried about speaking in English, don't worry, because a lot of people on the call be in exactly the same position and you're amongst friends. So Darlene, I think your hand was up, and then Armel.
Yes, Finlay, thank you so much for the presentation. There is a strong statement that's always made, which is the engines are getting quieter, and this is supposed to make us all feel good. What I understand is that arrivals, especially with next gen, there's no impact on the quieter engines with hundreds of planes overhead. Departures, there could be some influence, and for at the airport, there could be some influence. So that's one data point. The second is your last slide about, even though the plane might be quote unquote quieter, there are more loads, they're longer range, and the temperatures. So I think the question that I have is, given all this, really are we experiencing less noise, even though the engine is quote unquote quieter?
Yeah, so I think so one aspect is like the noise, we have been so far able to, for the same conditions, reduce the engine noise with time. And I think the point I'm making here, the point I make right at the end is that there are other operational things that might increase. Obviously, you might make each aircraft slightly quieter, but then the way that you operate them, you make them then loud again.
Yes.
But also then there's the number of aircraft as well. So, and how many aircraft there is in the sky and how many takeoffs and stuff that could cancel that out. But the kind of point I'm making here is just that the noise improvements that we've got in the past, by improving the way that we tune the engines with the acoustic liners, and we're kind of like at a point where we're going to lose the ability to do that because there's less and less space for them. So the historic trend of making engines quieter, it might be more difficult to do in the future, particularly given what we might need to do to get the next fuel efficiency that's also been promised.
Thank you.
Yeah, thanks, Darlene. And just before I bring Armel in, that's an interesting point, Finlay, because essentially what you're saying, the current technology, we've almost gone as far as we can. And the next step is the rather controversial open rotors, where the noise problem could be significant.
Yeah, so I don't think an open rotor realistically probably won't see it before 2035 at the absolute earliest, probably not until after 2040s. When I was making this presentation earlier, I found an article from 2010 that said that we'd have them by 2025, and actually we're almost at 2025 now, and they're nowhere near being developed. So I wouldn't expect really in the next 15, 20 years for them to come in anyway. That's why I was kind of talking about the geared turbofan and variable pitch fan, which we might see sort of geared turbofan. We'll see those. Well, there is one from Pratt & Whitney on small aircraft. There isn't any on large. We might see a large one by 2030. and then variable pitch fan in the 2030s, and then open rotor maybe 2040s. So there's kind of steps to it, but if they wanted to go faster and they wanted to make the open rotor earlier, we'd have this problem of noise. So it's kind of saying they can't really be optimistic on one without explaining how they're going to deal with the other one.
Excellent. Thanks. Armel, then Eric, and then there's a number of hands. We will come to everybody, but Armel next and Eric after that. You're on mute, Armel. You're still on mute, Armel. What I might do, Armel, is go to Eric and then come back to you, if that's okay. I think you may have frozen, Armel. So Eric, let's go to you.
Yes. I have a question for you, Finlay. You mentioned NOx at the beginning, but could you say the trend of NOx emissions for each of the solutions that are worked, because NOx is, as you know, has two impacts on ground air pollution and also on the non-CO2 climate impact.
Yeah, NOx is almost a separate topic, really, and it's quite complicated. But it's more to do with basically everything I presented now is to do with the propulsive efficiency part of the engine. But we've also got the engine core, which is the combustor and the turbine. And it's really the design of that influences how much NOx is produced. So you go to higher pressures and temperatures, and really a lot of the engine manufacturers have put a lot of effort into making the combustor and the turbine as hot as possible with advanced materials. But we're at the kind of limits of that, and that's why we're going to have to go into the propulsive stuff now, where the engine becomes quite different. But yeah, I mean, one of the main things with the combustor, for example, is lean burn, where you vary the amount of oxygen to fuel and ensure lean rather than rich burn, for example. But there's also stuff to do with the combustor design and the way that the fuel mixes. So yeah, it's another constraint. That's another thing to balance. Because if you didn't care about NOx, you might design the combustor differently for higher fuel efficiency. But so it's another complexity that it'd be difficult to get into without lots more slides. I don't think there's necessarily a trade-off between NOx and noise, because it's more about the combustor. So there's only some things, like the lean burn combustor can rumble more, which produces this like low frequency vibration. But I think that's manageable, and it's as I say, it's probably a bit too complicated to get into in more detail.
Okay, thanks, Finlay. Armel, I think you've come back to life, have you? You're on mute again.
Can you hear me now?
We can. You're loud and clear and alive again, Armel.
Welcome. Thank you, John. Nice to see you all, and thank you, Finlay. I've got two questions for you. Is it possible to have a new lighter material for a nacelle for safety, so that the blade would still be, inside as opposed to being out? And would you need to have new aircraft for those new engines? And third, looking at your crystal ball, when do you think these new engines and aircraft would actually be available in the future? Thanks.
Yeah, okay, so the first one was on materials. So we can make, as I said, nacelle gets bigger and it gets heavier because it's bigger. And one thing you can do is you can change the materials, go for lighter materials or a more efficient structure to make it lighter. Yeah, and we will do that. We will always use carbon fiber and titanium and the lightest materials going. It's just for a given set of materials, the bigger the volume is, the heavier it's going to be. So there always is, whenever we do another iteration on an engine, look at the best materials available at that time. But it's still, when you make it bigger, it makes it heavier. So there always is this improvement, and that's kind of what has meant that we could go bigger and kind of manage it, but we're at a limit. And yes, basically the engine affects the aircraft design quite a lot, particularly the engine gets bigger, we're struggling to fit them under the wings anymore, which is another reason to maybe move them up above the fuselage. It's handy having them under the wings because the lift force on the wing bends it up the way, and having the engine weight on it bends it back down. And also it's like near the center of gravity of the aircraft. So it's not the best moving them to the back. That's why most aircraft have engines in the middle. But yeah, so there's a lot of iteration that needs to be done between the aircraft and the engine. And at the moment, we've just had the same configuration of tube and wing aircraft with the engines in the same place, and lots of refining of that design. We're at a point now where we're going to have to move away from that because the engines are getting too big and they're changing and they're interacting with the wing. And that will mean that we need more radical aircraft concepts. But that'll take a lot more time, a lot more testing. And the timescales anyway are 10 plus years to do a conventional one. So it's going to take longer. So that's another reason why when the industry is optimistic about efficiency improvements, you have to look at the fact that we're going to need a big design change and that will take longer. So, and the industry is also talking about hydrogen and electric, and it's only got so much research and development money. So the more different things that they research, the less engineers they can put on each thing and the less money they can spend. So that's likely to slow it down. Plus we've had COVID and they've had a lot of losses, and they've had headcount reductions for engineers and stuff. They don't have me working there anymore, for example, but so like things will probably be delayed by COVID as well, which will push those industry timings back the way. So as I said, I think it'll be mid 2030 before, at the absolute earliest, that we'd see a variable pitch fan or an open rotor, and probably after that, probably more towards 2040.
That's really interesting, Finlay. Thanks for the questions, Armel. We will go to Arlene, Debbie on the phone, and then Mike, I see, has got his hand up. So we'll go in that order.
Yeah, there's also some questions in the chat as well from Carl.
Oh, is there? Right. I'll try to keep it. Thanks. I'll keep a note of them. Arlene, on you go. Welcome.
Welcome. Thank you. And thank you for this informative talk, Finlay. It brings me back years ago when I was a consultant to the New York City Transit Authority, and noise was a key problem in the design of an engine. And ironically, it was the fan that cooled the engine that was the problem. So I'm sitting here all these years later, and I'm hearing the same thing, that in order to cool the engine, you needed a fan, and that created other problems. And so you're looking into it. I have to tell you, though, that working with the engineers at the Transit Authority, we were able to deal with the traction motor. It was a traction motor problem, and it needed to be cooled. And so, ironically, a fan is the problem in not being able to curtail the noise, which was true with the transit situation with their motor. And I was just wondering, how carefully are you exploring how you could alter that fan? Because instead of saying, we don't have the space for it, we don't have the acoustic liners, what about the actual design of the fan that would make it possible to lessen the noise? So it was just ironic that I'm hearing the same thing that I heard at the Transit Authority, but they solved the problem and did design a quieter traction motor.
Yeah, well, we have been able to design quieter engines when compared back to back. So it's not that we're not able to do that, it's just that it's becoming more and more difficult. There is things that you can do with, there's some key, there's some key design constraints. There's the spacing between the rotating fan and the static fan outlet guide vanes. That's a big driver of the interaction noise between those things, and then how the number of those vanes compared to the number of the fan blades, and also the geometry of those. And those things are very heavily optimized the whole time to try and improve aerodynamics, and try and reduce noise, and try and improve vibration, all that sort of thing. But it's getting more difficult to do that because they're getting closer and closer. We have less space to work with, and the ability of an engineer to design something depends on the design space that you've got. And when that gets constrained smaller and smaller, you've got less room to move in to try and get an optimum solution, if that makes sense. So it's,
Yes.
It will always be possible to try and optimize it, but the room for optimization is going to get more difficult.
But it is being looked into.
Absolutely, always.
Okay.
Yeah.
Okay.
Excellent. Thanks, Arlene. We'll go to Debbie on the phone, then Mike. Then I think there's one or two, as Finlay said, there's one or two things in the chat which you may look at. But keep your hands, if you want to speak, put your hands up in one form or another. Debbie, welcome.
Yeah, hi. Can you hear me?
We can indeed, yes.
Okay, hello. I just have a question about when he's talking about this noise, whether or not they're considering different levels of noise. Like, are you just talking about the A-weighted sound level or noise and vibration? It seems like the trade-offs might be different levels of noise. And we're not sure. I don't know that we're not sure, but maybe we have a lot of questions about what is the most damaging to health aspect of noise. Is it vibration? Is it low frequency? Is it A-weighted? And these are different health effects that happen. I know that Arlene is an expert on this, and maybe she has answers too. But the other thing that I'm concerned about is it doesn't sound like there's ground level emission improvement. It sounds like as you go to these different types of configurations, maybe you're still burning the same amount of fuel at ground level. And I know pilots talk about coming in dirty. The arrival phase is very inefficient. So are those improvements, any of those, really affecting ground level emissions? And especially I'm curious about what creates the ultrafine particle. Is that if as you make the engines hotter, or you make this other chamber more with more pressure, does that create more ultrafine pollution? Do you know?
Okay, lots of questions there, Debbie. We would be disappointed, Debbie, if you didn't ask all your questions at once, because
Well,
you've got a reputation to maintain. Fairly quickly, if you can, Finlay, because
so basically, I mean, I'm not an expert on what different noise types causes what health impacts, so I'll skip that one. The more pollution, so basically ground pollution, particulate emissions, and when the aircraft's coming in, it's called idle mode, which is like the lowest thrust setting the engine can run at, and it's not an efficient, it doesn't burn much fuel, but it's not what the engine's designed for, and it's the lowest speed you can run it at without stalling the engine, basically. So it doesn't run that efficiently, and it produces more pollution, because the particulates, it's all about combustion in the combustor and how complete the combustion is, and therefore how few co-products, emission products are produced. because you're not producing pure CO2, you're producing carbon monoxide and all that sort of stuff. So yeah, and I think like one particularly interesting thing there is the fuel can help. So using an alternative fuel that has lower sulfur and lower aromatics mean you'll get better combustion and less particulate. And probably that is the way to go, rather than trying to, it's difficult optimizing the engine for idle. You kind of have to design the engine for cruise, and then you end up compromising it for idle because it's so far away from your design conditions. So that's why I'd say from that perspective, policies requiring you to use alternative fuel when you're on the ground and when you're near ground level could be an interesting thing to look at.
Thanks, Finlay. Mike.
Just late on in your slides, you showed a picture of an EasyJet with, I think, an open rotor. Is that to say that that's what they're thinking of doing? Because at the same time, they're promising us electric planes. I don't think it was quite next year, but, you know, in the very near future, I have a sort of cynical view that the only thing that interests the plane runner, the aircraft people, is how much does it cost to make and how efficient it is. And the noise comes very low down in the questions.
Yeah, and I think EasyJet have a lot of concepts that they've got on their website that that it's just a pretty picture and there's not much reality behind it. So it's the same with this open rotor. You know, they'll think that others say, look, we're working on this. We've given this university project £2,000 to do a study and make some diagrams, but we're not researching it in any way. And it's the same with electric. You're right. There's a company called Wright Electric that are claiming by 2030 they'll have a massive passenger aircraft, but it's completely unrealistic. And it involves aluminium batteries that don't really make sense. So yeah, I'm quite skeptical about EasyJet as well.
Can we quote you on that?
It's all on record, Mike.
Yeah, you can quote me on that for sure.
Listen, let's just go through one or two. But before the chat, let's just take Mikael, because you got your hand up.
Hi, yes. Thanks, Finlay, for the presentation. Can everybody hear me?
Yeah.
Yeah, great. Well, you sound very optimistic, but basically what you're telling us that in our lives, we are not going to see any planes, especially with jet engines, that are going to be more silent, just a little bit more efficient. And I just want to take 1 minute and think about that.
Yeah, well, no, I mean, they are getting more efficient. And what I'm sort of saying that we should be challenging the industry on is when they make big fuel efficiency claims and big noise claims at the same time. I think if you want more fuel efficiency, you might have to compromise on noise. If you want better noise, you have to compromise on fuel efficiency. So being very optimistic about both things. If they want to do that, we can ask them these questions and say, well, tell us how you're going to get that fuel efficiency improvement, you're going to need an open rotor. How are you going to, in order for us to believe you, you're going to need to tell us how you're going to make that quiet. And that will be difficult for them to do. So it's really kind of providing you with some questions that you can ask them that will be hard to answer.
Thanks. This is very valuable. Yes. This is valuable.
It's not to say they're not going to get a bit more efficient and a bit more quieter. I'm sure they will do to some degree. It's just becoming more and more difficult to get the same improvement we've got in the last 20 years in the next 20 years. And then there is an element, though, of we could go to smaller aircraft that fly less far with less passengers, and we could go for distributed smaller engines if we have electric or hydrogen. And there is a possibility with them because we completely change the design of the aircraft, and there's more possibility there. But those aircraft just they aren't ready yet. And
that's all 20, 30 years from now.
Yeah. So if you look at an airport expansion plan, it will be business as usual aircraft. So unless they're saying we're going to completely switch in 10 years' time, we're going to design our aircraft for those sorts, our airport for those sorts of aircraft, then they can't claim benefits from those sort of things. But that is one way, that one thing is if we had smaller, slower, quieter aircraft, more likely propellers rather than turbofans, and distributed propulsion, so smaller individual fans, that could provide benefit. But yeah, it's a long time off still.
Thanks.
Okay, thanks for that. We are running short of time, but there's one or two things in the chat. What role do newly developed fuels play in this context? You covered that to some extent, actually.
So the fuel is more about the emission saving that happens in the fuel production process, for these airlines to claim that there's a CO2 reduction. There is a non-CO2 improvement. It's what we were saying earlier about particulates. But that's more of a health improvement, and it's a global warming improvement because there's less contrails. But I don't think it will make that much difference to noise, apart from they're slightly more efficient. But I think it will have a relatively small impact. And how do these new rotor shapes affect the amount of non-CO2 emissions? They don't really affect it because it's more to do with just the combustor efficiency. Those, sorry, non-CO2. So yeah, the non-CO2 is more to do with the exhaust from combustion. So the rotor doesn't really make a difference to that. Although the one thing that's different is when you go to higher propulsive efficiency, you do get a slightly lower exhaust temperature, and that actually means you produce slightly more contrails at a given altitude. And we do see this as aircraft get more efficient, they produce contrails lower down, only slightly. So the CO2 improvement's worth getting, but it is something I've raised before, is when you consider fuel efficiency going up because of the rotor, we might see slightly higher non-CO2 as a trade-off as well. That's a bit complicated, so if you didn't follow, I can provide a reference for that if you want to understand it more.
Why don't you just go through the other points? Yeah.
So are there calculation tools that allow airlines to easily calculate which weight occupancy their aircraft would fly as quietly as possible and with the least impact on the climate? So this is the thing, like if you put more, well, the first thing is in terms of the range, there is a design range for an aircraft with a given payload that's its optimum range. And if you fly an aircraft a lot further than that or a lot shorter than that, then if you're shorter, your takeoff and climb is a bigger proportion of your flight, and that's not very efficient. You go longer, you end up having more fuel on board to fly further, and you end up burning more fuel throughout the flight, and it's not efficient. So there's like a most optimum range to fly a given aircraft. But then, yeah, if you put more passengers in, it makes it more fuel efficient because you're cramming more people in, and you don't burn that much more fuel. But that will mean that for that aircraft taking off, it will be heavier, and it will produce more noise. So this is what I'm saying. There's like a trade-off there between efficiency and noise for that aircraft. And basically airlines will just operate within, as long as they're meeting the noise requirements and getting away with it, they won't really think about it. Okay, Martin's left, and then Bertold, what is the difference between turboprop and open rotor? Yeah, it's more an open rotor is designed, like basically a turboprop is designed to only fly below a certain altitude, and if you go above that altitude, then because you've got these propellers that are just going round and there's nothing to slow the air down, you get supersonic shocks. Basically, the air goes above the speed of sound, and that creates a big efficiency loss. So turboprops can't fly beyond a certain speed, so they fly slower and they fly lower. Whereas an open rotor is more designed to operate like a gas turbine and fly at higher altitudes. And then they have to have like special blade design to be able to do that. But it is kind of like a bit similar when you've got a counter-rotating propeller or an open rotor. But one of them is more like a fan blade and the other one's more like a propeller blade, which are they're a bit different. But yeah, this is the thing. Like that A400M plane you're mentioning, which is a propeller rather than an open rotor, but it is it doesn't have a duct on it. It makes a lot of noise, and it's very heavy, so that's why it's so loud. So yeah, that's consistent with my understanding.
I think that's the questions in the chat, isn't it? Yep. Anybody got any final thoughts or questions before I hand back to Dominique? No. In that case, thanks very much, Finlay. That was really tremendous stuff. And I'll hand back to you, Dominique, to close.
Thank you, John. Just a few thoughts, with an average of less than 0.1 dB per year, we will only reach a significant reduction after a very, very long time. And we really need a technological breakthrough to obtain a good result in reduction of noise. And I was not very optimistic hearing what you had to say. And you mentioned ACARI, and ACARI goals are industry set goals. And when they don't reach the goals, they just postpone the time when they will reach them. So, it's only an intention to reach something which they don't always reach. Well, thanks a lot, Finlay, to have made drag over thrust and the impact of new engine and aircraft design on noise and fuel consumption understandable even for me today. This was a very interesting presentation, and the discussions and questions were interesting as well. Our next webinar will be on the Monday, 20th of June, 6 o'clock Brussels time, like always. And it will be something different and interesting as well on how to deal with our governments. And the format will be such as we will need the participation of everyone if this is possible. And it will be presented by Wouter. Wouter is a Dutch residence near Amsterdam Airport, Schiphol. Sorry, my voice is going. And I hope you'll be many to follow this next webinar, Monday, 20th of June. Have a good evening. Thanks all for attending. And bye-bye. Thank you, Finlay.